in business. Is this the control? All right, here we are. I'm sorry, I'm not listening to you anymore. Here we are. This is week 9. This is where we're at. You ready? Related population. Now let me explain something real quick how important this one is, because this is actually this is used probably more often than the others. And I want to give you an example. Whether you believe it or not, some of you in here are going to go on and say, you know what? Wow, this job's great. And they're willing to pay for me to get a master's degree. They're paying my tuition. I think I'll go back to grad school. Well, almost all grad programs ask you to do a thesis. And part of that thesis, you have to prove you can apply statistics to research. That's what a master's thesis is all about. A doctorate dissertation is even bigger, that you're applying statistics to research. So one that's very commonly used in a master's thesis is this related populations one. Let me give you an example. I had a colleague that was going for her master's or doctorate or whatever it was, many years ago. And I happened to just be starting to teach. And she asked me to be one of the sample of like 30 teaching professors that were willing to record themselves as they're giving a lecture. So we all had to, and back then this was a tape machine, so you can tell me how many years ago this was. You know, cassette tape, you guys remember those? Seriously, do you really know what a cassette is? I just want to make sure. Because this story, okay. So I'll hit the record button on the cassette and I give my lecture, and then you hand the cassette in, and everybody hand their cassettes in. Now, here's the deal. Then, we all agreed to do this online training. And we all did this online training, and then after the training, we had to record our lectures again. Meanwhile, the student who's writing up this paper, I want you to notice what this experiment's all about. They were counting how many, I can't remember what they're called, but where you're going or you're going, you're just saying things that make the speech kind of, filler words or pauses that don't make sense or something like that. They're counting how many of those take place. And then you go to this training, which is supposed to be how to keep your flow of your speech going and stuff like that. And then they count it again afterwards. Now, why is this like this? Because look at this sample was the same before as it was after. This is a classic what's called before-after experiment. And they were counting, what do you think that what was happening is the researchers saying this training should cause these teaching professors to even have better lectures by having less of those pauses. So I want you to think about this. If they're counting the pauses and the filler words that don't make sense before this training and then counting them after this training, if that training was having a true effect, would the number go down or up? Down. And so this number, this formula here, figuring out that t statistic, that top number is called the mean difference. That is a perfect example where it would go down and be a negative. Wait, am I right about that? No, positive. There'd be more of them before than there was after. So let's say there was 10 before, 7 after. Subtract them, the difference is a 3. So that'd be a positive 3. But here's the deal. You have to subtract the before and after for all 30 in the example, and then add up all those differences and divide by 30 to get what's called the mean difference. That's what that number is. This is called the mean difference. Before and after, the same related population, nothing's changed. It's the same teaching professors teaching the same course, giving very similar lecture, but after they went through this training. And so the whole idea is, did the training have an effect? Now remember, randomness could have made there be less of the awes and the things, whatever, fillers. So there has to be significantly less of them after the training for this training to be proved to be effective. That's what this is all about. So there happens to be an example in here. Now, here's the deal. There's Z and there's T, just like we've had before. I want to refresh your memory. Let me show you where we're at here. Come on, right here. Remember this? Before today, it's been all about 2 samples from independent populations, not related. And there was Z, and there was T, and there was another T. Here, this is all about related samples now, from like the same population or similar populations. And there's a Z and a T involved. And then we're going to proportions, which is always Z. But here we are on related samples. So now, there's Z and T. But, here's the good news. Let me get to it. Is this it? There it is. Here is the Z formula. But what I do with this formula is that's always 0 for this class on the right. Just like the previous formulas, that's always 0. So all you have is the mean difference. You guys whisper. All you have is the mean difference then in the numerator. You don't even have that. You're always going to subtract 0. It's always going to be the mean difference anyway. Just take that right out. So I'm eliminating that from the formula. This is the standard deviation of the difference. And this is the sample size, but it's how many pairs. Do you get it? It's not how many samples, because you have 30 teaching professors in that experiment and the same 30 after. That wouldn't be 60 in the sample. It's how many pairs. How many were before and after together. So that'd be 30 in that case, not 60. Go ahead.
Is it the same for Z and T?
I know. I'm pointing this out to show you that it is the same for Z and T. The only difference is that standard deviation of the difference. This one is the population. But I want you to ignore that. We're not even going to do Z in this class. We're not going to do it. Matter of fact, there isn't any problems from the book doing Z. There isn't any examples in the book doing the Z, because it's so common for us to have to do T. For us not to know the standard deviation of the differences in the population. But we always can get the standard deviation of the differences from the samples. But it's a tough calculation. I want you to see it. So we're just the Z, I wanted to point out to you. The problem would have to say, and we know the standard deviation of the differences of the population is, but that's not going to be there. I'm not going to try to trick you, because I can't even, there's no examples in the book, there's no examples in the PowerPoint. We're going to just focus on this one, which is T, which is this formula, but I took this out. This will always be 0. We expect, if there's no difference before and after, if all of the teaching professors had the same amount of ohs and filler words before as they did after as they did before, that would be 0. There would be no difference. So 0 minus 0 would be 0. You just ignore this right side. We're only using the mean of the difference. This is, see, now this is an S instead of that population symbol. It's the sample symbol. Standard deviation of the difference. That's what that D means. Standard deviation of the difference, which I'm going to teach you how to calculate. That's the square root of the number of pairs. Number of pairs, not the sample size. How many pairs are being looked at? Now, this formula in the bottom right, first of all, yeah, degrees of freedom. However many pairs minus 1 is your degree of freedom. However many pairs minus 1 is your degrees of freedom, which you need for your critical value and your p-value. Now this calculation on the right here looks like it's a big deal. I'm going back to 301. This is very much like a calculation for variance for 301, and it's not a big deal. You just do it one step at a time. And this is how you find the standard deviation of the difference. You're going to see an example of it. And I posted the detailed calculations, how to get this number in a picture on Canvas, so in this example you're about to see. But the calculation is just finding the mean of the difference and subtract that mean from every one of the differences. Then take each one of those subtractions, square each one of them one at a time, then add them all together, then divide them by the number of pairs minus 1, which is also the degrees of freedom, then square root the whole thing. That's how you find the standard deviation of the differences. And here's the example. You ready? I'm going too fast. Any good stories? Okay, let's keep going. This is the confidence interval for T. It's right here. The mean of the differences, plus and minus the critical T based on the significance and the number of tails. The standard deviation of the differences over the square root of the sample pair size. How many pairs? Sample pair size. The sample size of the pairs is what I should have wrote. There's the confidence interval. There's the test statistic. Now that you have those two, you can solve these just like any other problems we've been learning. Using the critical value approach, using the confidence interval approach, using the p-value approach, they're all right in front of you. And now, how are the null and alternative hypotheses written? They're not one mean minus another mean being equal to or not equal to or less than or greater than. It's just the mean difference. The mean difference being greater than or less than or whatever. So in this case, the hypotheses are written like this. The mean difference is less than, the alternative would be less than 0. That means the null would be greater than equal. The mean difference being greater than 0, if that's the alternative, the opposite would be less than or equal to 0. And if the alternative hypothesis for the mean difference is that it's not equal to 0, the alternative would be equal to 0. This is your two tails, those are your one tail. Very much like you see in this point, the difference is you don't have one mean minus another mean on the left. It's just the mean difference. Because it's the average of the means of the differences. It's the average of the differences. Here it is. We have 5 employees. And these 5 employees went to some kind of training, but before or after. Now, I want to give you a true scenario. A manager would use this exact situation when they want a ton of money for some special training they want for their staff. Let's say you have a crew of 100 employees. The amount of money it would take to send all 100 employees to that training would be thousands and thousands of dollars. So in order sometimes to justify this expenditure, you just maybe say, okay, let's randomly, and this is the key, randomly pick 5. You can't say, well, I'm gonna pick these 5, which I know will improve them, so I can get that money. No, this is the whole point of the experiment. You randomly pick 5 of the employees. You say, okay, without the employees even knowing it, we've been counting for all the employees how many complaints there have been over a certain period of time. And look at before, 6, 20, 3, RK at 0, 4. But remember, we don't know, we're not picking employees that happen to have a lot of complaints or very few complaints. This is random. The 5 employees were picked at random. Then they went to the training, and here's their number of complaints. 4, 6, 2, 0, 0. Notice, did they all go down? It looks like every one of them went down except for the 0. But did they go down enough to have significance to prove that the training caused it? Or was it just randomness that made them go down? Possibly because it's a different set of days. It's the same employees doing the same job, same type of customers, everything's the same, just different time period after the training. This is what's called related populations. Matter of fact, this is before, after, a classic before-after experiment, like I explained to you. This chapter right here, this section right here, I remember a friend of mine years ago, like 20 years ago, said, look, I'm going to go get my master's. Can you help me? Can you help me? He was a basketball fanatic, loves sports. He loves basketball. He wanted to prove that a player plays their butt off and has great statistics just before becoming a free agent, because they want to maximize the amount they can get a contract for becoming a free agent. So he did a classic for his graduate thesis, did a classic before and after experiment. He went and he randomly picked. He got the list of all the players that were last year going to go free agent, that went free agent. Excuse me. He got the stats from them. Randomly picked like 10 of them. Got their stats before. Got their stats after being free agent, because now they got the big contract. They don't want to get hurt. So they're not necessarily. His whole assumption was the alternative hypothesis is that their statistics would go statistically down after getting the big contract, because get the big contract, they're playing their butts off and the stats are higher. That was his alternative hypothesis. The null would be that the stats are the same, or if anything, got better. That would be the alternative. So it was a one-tail. But he's applied the exact statistics you're seeing right here and got his master's degree. So you can see how easy this is once you figure this out, how to do this. And everybody in here can get their master's, because this is the hardest part of getting a master's. The classes are actually easier than your bachelor's degree. It's the thesis that kills people. Mine was like 162 pages, but it was a whole different subject. You got to do a bunch of research, to prove it. Has anybody studied this before? You got all that stuff to go with it. But this is the part that everyone else finds hard, right here. So now, here's the deal. We take how many complaints after and subtract it from before. We got -2, 6 minus 4, -2. Well, that should have been +2, shouldn't it? Oh, we're going after minus before. Here we go. After, that's where maybe I got it confused. After minus before. So 4 minus 6, negative 2. 6 minus 20, negative 14. 2 minus 3, negative 1. This should be working out as a negative number because we're supposedly going to have less complaints after the training than before, so that makes sense. But to find the average of the difference, we now got to divide that 21 by how many pairs we had, which is 5. So 4.2, there it is. 4.2 is our mean difference right there. We now are going to have to find our standard deviation of the difference. We got to use this negative 4.2 and subtract it from every one of these differences. Negative 2 minus negative 4.2. Negative 14 minus negative 4.2. Every one of those gets subtracted. Then we take all 5 of those differences and square them each. Then we add each of the squares. Then divide by 4, right? 5 minus 1. Then square root it to get that 5.67. I want you to see how that's done. Once we have that mean difference, we do this. Negative 2 minus negative 4.2, then square it. Negative 14 minus negative 4.2, then square it. And so on, and so on, and so on. There's all the squares. There's all the squares added, 128.8. There's all the squares added divided by the degrees of freedom. 5 pairs minus 1, 4. Now we take that number and square root it. There's the standard deviation of the differences, 5.67. Does everybody see how that was gotten? That takes a lot of time, so the odds are that, as a matter of fact, I believe on your homework, you're given the sample standard deviation of the difference. So look for that, realizing you don't have to do this. Everybody hear that on the homework? I believe, I'm almost sure, matter of fact, we better take a look. Right. Here's your instructions. We have a written in Excel this week, just like last week. Same thing, due Tuesday, November 5th. November. Hey, don't forget to vote before you come to class November 5th. Sure. I'm serious. If you guys skip class to vote, then skip class. That's way more important than class. We're recording this. You kidding? Oh. All right, where was I? Homework, here we go. Did I give you the sample standard deviation of the difference on the homework? There it is. Sample standard deviation of the differences is 6.1 with a sample of 14 pairs. There is given to you. That whole calculation on your homework is given to you right there in that sentence. All right, so that now you know where that 5.67 came in. So you're about to see it plugged in to get our test statistic. And then I think we were doing the confidence interval. I can't remember. So this is the what? Negative 4.2. Standard deviation of the difference is going to be the 5.67 divided by the square root of the number of pairs, which I believe were 5. Square root of 5 pairs there, right? 5 sample pairs. We do all that. Oh, we got to get that critical. Excuse me, we got to get that critical value to compare it to. We're doing the critical value technique. So help me through this. What's the significance? We're using 1% significance. In order to get the hundreds of thousands of dollars to have the rest of the 95 employees trained, we got to prove with 99% confidence that this training caused the employees to have significantly less complaints. That's what you're being said when you choose a 1% significance. Now, this is a big deal because you must be asking for a lot of money, hundreds and hundreds of thousands probably. So with 1% significance, how did we get that critical value of 4.604? Help me out. Equals, what's next? Excel, help me. Come on. How did we get that critical value? 4.604 equals
T.
T.
INV.
INV, very good. Parentheses. One tail or two tail? Two tail, very good. So what do we have to do with the significance in the first number? I can't hear you. Do we have to double it or do we leave it the way it is? Do we double it or leave it the way it is? You guys gotta check. You gotta check your cheat notes. Where are your cheat notes? Come on. You think I have this stuff memorized? I'm an old man. I can't memorize anything. I need help. So what would be the if we don't have to double it, which with two tail, I don't believe you do.
No, it's just a significant.
That's right. So what would be the number here then? There it is. There it is. Comma. Degrees of freedom. Very good. 4 it is, because there's 5 pairs minus 1. And do we do tails on this or no?
No.
This is it right here? Okay, boom. Equals, and if you put that in there, you're going to get 4.604. All right, our test statistic. We did this whole formula, and we got negative 1.66. Don't forget, even though we went ahead and got a positive result from Excel, we know this means negative because we got a negative thing we're going to compare it with. So you don't have to sit there and go, wait, this is positive, this is negative. We just change it, just make that negative. You compare negatives to negatives, positive to positives. If you think of a number line, is our test statistic 1.66, negative 1.66, inside closer to 0 or outside negative 4.604? Is our test statistic inside or outside? Inside, which means we can or cannot reject. Cannot reject the null hypothesis because our test statistic is clearly inside. If you look at the number line here, here's 0, here's the 1.66, there's the 4.604. We're clearly inside, so we cannot. T-stat is not in the rejection region. Do not reject the null hypothesis. Help me out. Let me see it. Is critical value on here? No. Critical value. Here we go. The mean difference. I see it up there. The mean difference is negative 4.2 plus and minus the critical T. We calculated. I see it right there. 4.604. Is that right? 04 times. Now I have the standard deviation. The difference. There it is. 5.67. 5.67 over the square root. How many were in our sample of pairs? 5. There is how you find the upper and lower critical, confidence interval, which I did right here. Is this it? This is not it. Is this it? No, this is not for this one. Where is it? Oh, wait, what slide is this? 33? I got this all done and posted for you. Hang on. 33, right there. Here's the confidence interval. Negative 4.2 plus or minus 4.604, 5.87 over the square root of 5. I did all the math on it, and I got negative 15.875 and a positive 7.476. There's our confidence interval. You must determine if 0 fits in that confidence interval or not. Look at it. It's negative 15.8 and positive 7.4. Does 0 fit between those numbers, yes or no?
Yes.
Yes. And any time your null hypothesis number fits within the confidence interval, you either can or cannot reject. Cannot reject because the 0 fits. There you go. So we did critical value right here. We did confidence interval. All we have left is p-value. Let's go. Let's do it. Boom. P-value, Excel equals T, D-I-S-T, parentheses, 1.66. Was that our, 1.66. I dropped the negative, if you notice, because when I use T, D-I-S-T, you drop the negative, comma, 4 degrees of freedom, comma, 2-tail, parentheses. The p-value for the test statistic of negative 1.66 at 4 degrees of freedom is equal to 0.1723. This was at 1% significance. 1% significance. Is our p-value of 0.1723, 17.23% to be exact, is it telling us that we can or cannot reject? Cannot reject because it's larger or greater than our significance of 1%, 0.01. Because it's greater than, we can't reject. All 3 ways of doing it, whether it's critical value, confidence interval, or p-value, all came up with the same solution. We cannot reject.
Professor?
Yes.
So this is for T? So
All T, because we're not going to do Z.
But last week, what did we do?
No.
The 2 previous
This is for 2 samples from the same related population. Last week were 2 samples from independent populations, which have both Z and T.
So are you going to tell us that on the exam?
No, you got to recognize it. That's the whole point.
How do you
guys,
recognize it?
when you're reading the questions, matter of fact, that's what I think we're going to do on Thursday. Is I'm going to bring up like 6 questions, and you got to tell me, where is this from? Is it from not independent populations, or is it from related populations? Am I using Z or am I using T? All right, so that would kind of help then, because that's probably the most important part of the quiz. Okay?
But we're not using Z, right?
Not for related samples, yes, related, just for this particular case. Let me go back real quick to show you. I want you to see this. This one was all about last week with this one where we had both Z and T from independent populations. But this one is related populations, we're only gonna be doing T. And this one is proportions, which we'll only be doing Z, which is next week. Okay, I want you to see another example. So, we're gonna go to, let me find it here. Page 358 on your book. I didn't open the book up. Hang on here. Find it real quick. I know we got it right. Okay, example 10.5. Here it is. A manager is interested in improving productivity at a plant by changing the layout of the workstation. For each of the 10 workers, here we go, each of the 10 workers, she measures the time it takes to complete the task before changing, and then again after the change. So picture that. You know, hey, we know this change of this whole structure, this manufacturing line, operations management, is gonna be changing. So we're keeping track, we're trying to find the average amount of time it takes for these 10 random chosen employees before we make the change, and then again after to see if there's a difference. Did the change of the production help productivity? Now, if we're using time as the indicator, think about a stopwatch or something like that, some kind of timer. Would you think that if you're the manager who's come up with this new design, would you want that time to be increased or decreased after the line's been changed? Decreased. You want to increase productivity, which means it takes less time for the task. So you'd be measuring before and after. We just found out we're taking the after minus the before. So if it's decreasing, we want that time to decrease. We should end up with a negative. Mean of the differences should be negative because it'd be a smaller number minus a bigger number for most of them. Let's take a look. So it says, for each of the 10 workers, we measure the time it takes to complete the task before and again after the change. She calculates the following summary of statistics. The sample difference is 8.5. It's not even a negative. It's 8.5. So something looks suspicious already. The S sub D, that's the standard deviation of the difference for the sample. It's given to you. I will give it to you in words if this is a quiz. It will say the standard deviation of the sample standard deviation of the difference is, in this case, 11.38. That's pretty large, by the way, 11.38, considering the difference. And then N equals 10. That means the number of employees before and then again after is the number of pairs is 10. We have all their information to plug it all in right here. The mean difference, the sample standard deviation of the difference, and the number of pairs. We plug it all in. How's it asking to solve? Use a 95% confidence interval. So we're going right over here to this confidence interval. At 5% significance to get we gotta find our, let's see what our critical value is. The critical value they got is 2.262. So it's 8.5 is the mean difference given to you right there. 2.262 is the critical T. Here we go. Let's get that critical T. Equals T, I, N, V, parentheses. It was 95% confidence. Is it two tail or one tail? Does it say? Looks like it's two tail. Let's keep going. Assume it's two tail for now, so that'd be 0.05, comma. What's the degrees of freedom in this case? 9 it is, comma, equals. It should equal 2.262. 2.262. If it doesn't equal 2.262, we may have misinterpreted the problem to be a one tail possibly. Would be the only reason why we might be wrong. And if so, we would just double that to 10% up front. let me look at my notes. It says use 5%, so it must be get 2.262. So there it is. Now, the sample standard deviation of the difference is 11.38 given to us in the story, divided by the square root of 10. Again, the number of pairs, the number of employees before and after were given in the story. We get, here it is, 8.5 plus or minus 8.14 gives us a range of, ready? 0.36 is the confidence interval lower range, and 16.64 is the upper range. My question for you is, does our null hypothesis mean difference fit between those two numbers? Yes or no?
Yes.
It does. Does it? Does 0 fit between those two numbers?
Yes.
No. Change your answers. Which is
I don't know.
it? Does 0 fit between 0.36 and 16.64? Neither one of those numbers are negative, so 0 does not fit between them, which means we have evidence to reject that it's very much possible. I forgot the story. What was it? What was before? That the change of the production process has had an effect on this. Go ahead. No.
How did you know it was two-tail?
You know, I'm not sure how I knew it was two-tail. I'd have to read it again to figure it out. Don't get me wrong, if this were a question on the quiz, it would be obvious, or a homework, it would be two-tail. Say that again. It says in order to construct a 95% confidence interval mean difference, we use blah, 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 blah. But in order to get this, see right there where they're taking the significance divided by 2, degrees of freedom, which is 9.02, they took 5% divided by 2 to look up this 2.262. If you were using the T-chart, which means it was a two-tail, but nothing in there says it. But if this were a homework problem or a quiz problem, it'll be obvious it's a two-tail or a one-tail. It's not like you have to guess by looking at those little numbers there. All right, so hang on a minute. What is that, 10.5? That was the confidence interval. We still got p-value. Let's do it. This is right here. Here's the critical value approach. Let me go back to that again. What was the T? We didn't calculate T, did we? We didn't calculate the T statistic. All we got is the confidence interval. All we know is that 2.262 is our critical value. So now we go here. 0.05 critical value. Wait. Oh, this is 10.7. We're on 10.5. Did I not post this? Oh, is it in here? No, it's not. Are we gonna have to wing it? I thought I did this. Yeah, yes I did. Let's do it. Let's do it right now. You ready? Let's get the test statistic. What's the mean difference between the two? 8.5. Over, what's the standard deviation of the difference for the sample? 11.38. And what's this, how many pairs did we have? 10. Okay, where's my calculators? Here we go. Someone's got to make sure I'm right. I'm going to start with the 10. I'm going to square root it. I get 3.1622, whatever. Now I'm going to take 11.38 and divide by it. I'm going to put this in memory. Watch out, I don't have to retype this. Put that in memory. Now I'm taking 11.38 divided by. Now I'm bringing that back out of memory. The 3.1622, whatever. Now I'm right here. I got these two right here at 3.59. Now this I got to write down. So now I have 8.5 divided by 3.5987. 5987. Look at my rounding. Is it 2.36? I can stop right now. Oh, I'm gonna have to confirm. I'm gonna have to confirm now. 8.5 divided by 3.59. Bless you. 5987 equals, you said 2.361, 2.36. What is it? Yeah, I'm gonna have to go 2, aren't I? Because the next digit is that 9, it has a bigger digit ahead of that even. So there it is. There's our T. What was our critical again? We'll go back to the story right here. There's our critical right there. Critical is 2.262. There it is. Here it is. Our test statistic we just calculated is 2.362. The critical is 2.262. Are we inside closer to 0 or outside the critical T by that number? What do you say, inside or outside? Outside. Does that give us evidence to reject or not reject?
Reject.
Reject, but look at how close. That's darn close, isn't it? All right, let's do p-value. Let's check how close this is. Ready? Equals T, what is it? D-I-S-T, parentheses. Help me out. Our test statistics right there, 2.362. 2.362, comma, what's next? Degrees of freedom? 9. Comma, what's next? One tail, two tail, or two tail? Is this two tail? You sure? Okay. You know what? I just realized I did it on the back here. There it is. Here's what we did. Yeah, I got T 9, 2. You ready? This equals 0.0425. What's our significance in this problem? 5%, 95% confidence. Is 0.0425 less than or greater than 5%? Less than 0.05. Does that mean we reject or not reject? Reject. Confidence interval rejected, our critical value rejected, and now our p-value is rejected. We're rejecting it. Reject, reject, reject. How are we doing? Doing okay. Since we're only focused on one thing, the T, on this week's homework, all you're doing is the T, you can literally almost have it done. Except for on Thursday, we're learning how to do the whole Excel part of it. But you're almost there. I got one more example ready if you want to see it. You want to see it? One more? No? You think you got it? Seriously? Wait, I hear that. Wait, I hear it. Some people say yes, some people say no. Let's just do it. I'll do it fast. We're going to 10.7. Same page, I think. Maybe lower on the page, down on the bottom, maybe. Wait, or 10.6. Which is it? 10.6. It is 10.6. We're doing this one. One tail or two tail. I don't even have to read it real quick. One tail or two tail? Two tail it is. Says using the example, blah, 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 at 5% significance, blah, 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 blah. Solution. Wait a minute, where are we? What is all this? In example 10.5, we found 95% confidence interval. Oh, this is doing the, this is just saying that the 0 fits between the two, so therefore, it says right here that the range was from 0.36 to 16.64. Although the interval is very wide, the entire range above, though, is above the hypothesized value of 0. 0 doesn't fit between the two numbers. We came to that conclusion. Therefore, 5% significance level, the sample data suggests that the mean difference differs from 0. In other words, there has been a change in productivity due to the different layout of the workstation. The bad news is, though, is that it takes longer. A positive number, right? If you're subtracting the after from before and you get a positive number, that means it took longer after with the new layout. That's the bad news, because we were able to reject the hypothesis. All right, let's go to 10.7. Let's revisit the introductory case. Recall a local ordinance requires a chain restaurant to post calorie information on their menus. The nutritionist wants to examine whether average drink calories declined at Starbucks after a passage of the ordinance, okay? So let me make sure you realize what's going on here. The ordinance, so you're going to Starbucks, you order whatever the beverage is, you drink it, there's no information, there it is. Now this ordinance passed, and maybe right on your cup or on the wall on a sign behind the counter or somewhere, they have to put how many calories every single item is that you could possibly order. And I guess the researcher is trying to see if there was a decline, meaning by people being aware of the amount of calories now that they're consuming, are they going to reduce their calorie intake? That's kind of what the researcher is saying. So this is the one tail, right? Matter of fact, if we scroll down, there it is. The mean difference, now I want you to think about this, the researcher's trying to say, will they decrease their intake of calories? So if someone's taking in, let's say 100 calories before, and it decreased it down to 90 calories, and our formula says to take the after minus the before, this would end up equaling -10. And we'll have all these negative numbers. We add them and divide by however many is in our sample size, it should give us a negative mean difference, right? So our alternative hypothesis would be that it's less than 0. So this does not make sense, does it? It almost as if it's the before minus the after. So get that figured out, will you, before the quiz? Did you like that? That's a real assignment. So here it is. It's a one-tail. The mean difference is greater than 0. The null hypothesis would be that the mean difference would be less than or equal to 0. We're going to go ahead and assume that they're doing it the opposite way than the PowerPoint. So here we go. We looked at each one. It says normal conditions. The test will satisfy since the sample size is greater than 30. Remember, that is the golden rule in sampling, that the sample size should be 30 or larger. That is kind of the golden rule. The value of the test statistic determined by, there's the equation, where it equals 0, blah, blah, blah. What do we get? Consumes 141 calories prior, 142 calories after, for the difference of -1. The difference of the proportion of the other customers appear in the 4th column of table 10.5. So there you go, there they are, all the way down. There's 40 of them. Here's all their differences. -1, -3, so look at, they're taking the before minus the after in the book. Before minus the after, not the after minus before, the before minus the after.
What are we supposed to do?
So you do it either way, as long as it makes sense to your hypothesis. And it does. If you take before minus after, this would be plus 10, this would be plus, this would be plus. So your alternative hypothesis should be greater than 0. But if all these are going to end up being minuses, 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 it'd be less than 0. Now, how will I know what you're doing? I'll see if you're taking 141 minus 142, or are you taking 142 minus 141? Are you getting all negatives, or are you getting positive? And I'll know what you're doing. But if you all want to do the same thing, then agree right now which way you want to go. It's up to you. Either way works.
Where did they get the before and after numbers from?
Before and after, you have to kind of imagine that they were collecting the data somehow from 40 different people before they decided to implement this ordinance that got voted on. So what they're saying is, hey, we know these 40 we have these random 40 regular customers. We're keeping track of how many calories they're drinking before by their orders, and then how many after. I don't know, it's really a weird experiment because without a lot of details there, it makes you wonder, how did they get the exact calories? Did someone order a smaller one? Did someone order a bigger one? Or are they literally seeing if there's any left over when the customer leaves? I mean, it's kind of a weird experiment, really. In either case, though, you'll be given the information. You'll be given the mean differences. You'll be given the standard deviation and most of the mean differences. But you're definitely given the sample standard deviation of the difference. On the test. You'll be given. Right. Yeah, you might. But barely. Yeah, just a little. If I had given you data like this where you literally are calculating the difference, or you're calculating definitely the standard deviation of the difference, then it's only going to be what, a sample size of 3, because it will just take way too long. So odds are you might be given this information. Yes. Let me ask this, on the homework, are you given the information, or are you having to calculate this? Well, there you go. I always write the quizzes based on the homework, right? So is that a relief? So here we go. We add them up. There was 80. The differences add up to 84. 40 customers. There's the mean difference. 2.1 calories more after than before. So they didn't reduce their calorie intake. They increased their calorie intake. 2.1. So the alternative saying is an increase. Now, looks like we're going to use, here is, you take 2.1, you have to take -1 minus 2.1 squared, -3 minus 2.1 squared, 6 minus 2.1 squared, and then take each of those squares, add them together, divide by the number of pairs minus 1 to get your standard deviation of the difference. That will be given to you, 66.5. Now you have all the information. You've got the 2.1, the 66.5. You know there's 40 pairs. Get your test statistic. There it is, 1.629. Let's get the P, are we going P-value? Looks like we're going P-value. Let's get the P-value. That's not on there. We gotta write this down. Equals T.TDIST. We just calculated the test statistic. 1.629, 1.629, comma. Degrees of freedom? 39, very good, comma. Let's stare at this again. It's a one tail, that's right, because it was greater than, that's right, one tail. We do that, and we are going to get a p-value of, there it is. Where is it? 0.0557. 0.0557. Here we go. Equals 0.0557. What's our significance? Do we remember?
5%.
5%, isn't it? Is this number, should I put it greater than or less than 5%? Greater than 0.05. Do we have evidence to reject or not reject?
Not reject.
Not reject. Our p-value is greater than our significance. Now, we have enough information there. All we don't have is the critical T in this case, but we have enough information. Once we got that critical T, we could do a confidence interval with that critical T, and we could do the critical value approach with that critical T, because we already got the test statistic. But we already know, since we couldn't reject here using p-value, that our critical value is going to say we can't reject, and our confidence interval is going to say we can't reject. Our confidence interval will not have zero between it. Meaning they're both going to be positive, they're both going to be negative numbers. Any questions? Do we feel like we can do the homework? Okay. All right. We've been lacking in life advice. Hang on, almost forgot. All right. So I want to tell you, if I go around